Yes. But we're going to continue that. So. All right. So. All right. So let's do a real quick recap of what we talked about yesterday, and then we sort of touched on big rule number 2, but we need to finish it. All right. So. Yesterday we were talking about projectiles. All right. We talked about what a projectile was. Basically, anytime an object is in free fall, it's a projectile. If you drop a ball, it's a projectile. If you throw a ball, it's a projectile. If you shoot a ball out of a cannon, it's a projectile. If you shoot an arrow with a bow, it's a projectile. If you fire a bullet out of a gun up into the air, it's a projectile. Okay? Because in all of those cases, after the object is released, the only force time is gravity. Good? Sure. All right. So that is that. So those of you who weren't yesterday, remember all the videos are recorded, they're online, so check my calendar if you're trying to write that down if you're absent yesterday. So then we talked about the 2 big rules of projectiles. This slide was white yesterday, I made it yellow.
Whoa.
All right, I know, exciting, right? Okay, all right, so big rule number 1. This is huge, you guys, you need to understand this. Big rule number 1 says that as your projectile travels through the air, the rate at which it moves from left to right, or right to left, or whatever direction it's moving in horizontally, that rate is constant. All right? We call that horizontal Vx. So big rule number 1 just says Vx is constant. The rate at which your object travels horizontally is constant. And I proved that to you in a couple of ways. We watched the video of the airplane dropping the bombs. As the bombs fell, where did they stay? Under the airplane, right? Because both the bombs and the plane were traveling horizontally at 200 meters a second, right? Okay? We also saw me rolling on a skateboard, and as I was rolling, I threw a ball up in the air, right? What did the ball do? Stayed with me, right? So it was just this. Right? Both me and the ball were moving horizontally at the same rate of whatever number we use. Good? All right, so that is big rule number 1. Are there questions about it? Dynamite. Okay, big rule number 2. My smartboard needs to be recalibrated. Oops. Why is it? All right, there we go. Big rule number 2. Any projectile will fall with a vertical acceleration of -10 meters per second squared, regardless of its horizontal motion. Right? If you wanted to write that in shorthand, it's this. An object's acceleration vertically, notice the y. What's the y telling you? Vertical, right? X would be horizontal, right? Thank you. Just in time, you haven't really missed anything from yesterday, or except for what we did yesterday. Okay, which we're reviewing. All right, so this means the acceleration vertically is -10 meters a second squared. That's big rule number 2. Okay, and so at the end of the hour yesterday, I posed this question. Everybody's okay with this? Do I need to leave this up here for a minute? Caitlin, you good? All right, so I asked you this question. I said, suppose we've got these cars all driving off of a cliff. It's all the same cliff. They all drive off the cliff at the same instant. Which one hits the ground first? All right? And the surprising answer is they all hit the ground at the same time. Okay? Because all of the cars, if they're moving, so we had car F was just dropped, right? So car F just goes, right? All of the other cars, they have velocity, but all of the velocity is horizontal. So they're moving horizontally, they're not moving vertically at all, right? And so what happens is, because there's no vertical motion, they still fall down. The only difference is they move horizontally while they fall down. So the one that's going 2 meters a second, we had decided it was going to take 1 second to fall, right? So the one that's going 2 meters a second, instead of going it's going to go and land 2 meters away. All right? Oops, it's labeled up. 2 meters. This one that's going 10 meters a second, it's going horizontally much faster, right? So in the time it takes to fall, it's going to go horizontally farther. But it still takes the same time to fall. So instead of going mirror or mirror, it's going to go mirror. Notice I had to make the line faster to get there, right? Because it's going faster. And it went 10 meters. Right. So it turns out that they all hit the ground at the same time. Even C, D, and E, which there isn't room for me to draw on the board. Because all of them are being launched horizontally, they don't have any vertical motion. So they fall down at the same rate. So, I should prove this to you, yes? I will do that now. If you're at home, you missed this. Yes. Okay, so, alright, so what we just saw there, if you're watching at home, look at the YouTube link. There you go, there's your link. How about that? So what we just saw is that regardless of how fast your projectile is launched horizontally, it will fall down at the same rate. So all of these cars and a bullet fired from the top of this cliff horizontally will all hit the ground at the same time, because they're all falling down at the same vertical acceleration of -1. Questions? Yes.
Yes, the horizontal velocity ui.
That is correct. How can you remember which one's horizontal and which one's vertical? X and Y axes, right? X and Y. I, for whatever reason, as a kid, always had a tough time remembering which one was horizontal and which one was vertical. Horizon. The horizon runs horizontally. That's how I remember it. Like, still, I'm 40-something, right? And that's how I still remember it. All right? So the horizon runs horizontally. That's your x-axis. Good? Questions? All right. So, will you please, if you have not done so, dig out your guided projectiles worksheet that you did while I was out at my meeting the other day. Oh, that is not quite what I wanted to do. Okay, so what we're going to do here is we're going to look at 3 objects. All right. The first object is a bicycle that's moving horizontal at a constant velocity. Just like every projectile, right? Every projectile moves horizontally at a constant velocity. Then we're going to look at a bike that we drop off of a building, falling down at -10 meters a second squared, right? Then we're going to combine the motion and have the bike roll at 20 meters a second off the cliff. All right, so here we go. Part 1 says, imagine a bicycle traveling at a constant velocity of 20 meters a second along the horizontal road. Number 1, assume the bike begins at a position of 0 and fill in the chart at the right. So, begins at a position of 0. Where does that go in my chart? Horizontal position is 0, right? Okay. Now, the velocity is 20 meters a second, and it's constant. So how do I fill in this horizontal velocity column? They're all 20. Good? So that's A. Is everybody good up to there? Oh, so now we got to fill in the horizontal position. So how do I figure out how far the bike goes? You're going 20 meters a second, right? So after 1 second, you're going to go 20 meters. After 2 seconds, you're going to go 40. There you go. After 3, 60, 80, 100. There we go. So there's our positions, right? Okay. So it says, now use the number line below to make a motion map. Mark the position of the bike each second with an X or reasonably sized dot. So at time 0, there's our position. At time 1, there's our position. Time 2, time 3, time 4, time 5. I didn't label my units just because I'm trying to save time. Make sure you label your seconds. All right? What do I want you to notice about this map? What's the same?
Uh,
What?
like
move on velocity. Or like, okay, it's gonna move the same amount like every second.
There you go. It moves the same amount every second. When I ask you those questions, give me detailed answers. Saying it's the same doesn't tell me anything. Are you saying the position's the same? Like the position was always 0? Okay, I'm not thinking any of it. I get these answers all the time. So when we get to the test, make sure that your answers are descriptive. We answer the question that's being asked. All right, so is everybody good with that? All right, so we did A, we did B, part C. Draw in your velocity vectors. So, V equals 20 meters a second, right? V equals 20, V equals 20, V equals 20, V equals 20, V equals 20. All right? Cool? I realized my mic was not set up, so I probably picked it together, but it might be muddled. Okay, are we good? All right, so that's that. 3, what's the acceleration? Why is it 0? The velocity is constant. It doesn't speed up, slow down, or turn. So the acceleration is 0. Follow? Everybody good? Anybody ungood? Excellent. So that is horizontal motion. These should all be labeled V is 20 meters a second. Okay? Probably should actually label them Vx, but I guess it doesn't matter. Okay. Bam. Here we go. So now we're going to take that same bike, but instead of riding it 20 meters a second down the road, we're going to drop it off of a tall building. And it tells you it takes 5 seconds to fall. So here we go. Imagine a bicycle that's being dropped from rest off the top of a tall building. Suppose the bike takes 5 seconds to hit the ground. Assume the bicycle begins at a position of 0. So my position began at 0, and my vertical velocity began at 0, right? Everybody good up to there? What words tell me that the vertical velocity begins at 0? Good, it says from rest, right? And then I know the position is 0 because it says it starts at a position of 0. Good? Those two numbers will not always be 0. They happen to be in this one. They don't have to be. All right, so we got to fill in the chart. So who can tell me how to fill in the vertical velocity column? Sure, what do you got, John?
It's just negative 10 meters per second.
The whole time, just like negative 10, negative 10, negative 10? You're close. You got the right idea. So the reason that negative 10 is important is that's the acceleration. So our vertical acceleration is negative 10 meters a second squared. All right? So, but that's not the same as velocity. All right? So remember on that last test I said, what does this acceleration tell you about the velocity? So what does this acceleration tell me about the velocity? What do you got, Stephen?
Isn't it going down by 10 meters every second?
What's going down?
Our vertical.
Vertical velocity is going to go down by 10
Meters.
close. What do you measure velocity in?
It
It goes down by 10 meters per second.
I was going to say meters in the first.
Yeah, so the velocity is going to decrease by 10 meters a second every second. So John, you had the right inclination that negative 10 is important. But they're not all negative 10. It starts at 0, then it goes negative 10, negative 20, negative 30, negative 40, negative 50. Does that make sense? Johnny, good with that?
Yeah.
Is everybody good with that?
So that goes with the acceleration, the vertical velocity.
Correct, because, yeah, so we know that that's true because this is our vertical acceleration. Clear? All right. Conceptually, why does this sort of make sense? What is this? What happens to the bike as it falls? Goes down in it. It's getting faster. It's moving down, negative velocity, faster and faster, bigger numbers. Right? The velocities are negative, so it's going down, and they're getting more negative. It's going down faster and faster and faster as it falls. Clear? All right. Now, vertical position. You got to calculate these. I will do 2 of them. Okay? So, let's find this vertical position. So if I want to find that vertical position, I need to start by writing out what I know. So, somebody tell me some stuff that I know for that 1 second that it took to get to that little red circle I drew. Good. Final velocity is negative 10. How do you know that, Maria? Because it's right here in the chart. All right. So no, but the reason I want you guys to understand it's not because the acceleration is negative 10. It's because the final velocity is negative 10. Follow? All right. What's the initial velocity, guys? 0. Good. How much time did it take to get from 0 to 10? 1 second. What are we looking for? Displacement, right? We got to figure out how far it fell. All right. We also know our acceleration. If you want, you can use that. So at this point, you can use any of those 3 displacement equations I gave you: the axe, the screwdriver, or the drill. Any of them work. Most of you seem to like the screwdriver, so we'll go with that. Displacement is 1/2 of VF plus VI times the time. So it's 1/2 of negative 10 plus 0 times 1. And it gives you negative 5 meters. We've done that before, haven't we? Twice already. We did it in the notes once, and then it was on a homework assignment. So we know all of these answers. We've done them before. This is now the 3rd time we've done these. So, what am I telling you? Yes, know them. For sure. Memorize them will make your life easy. All right, so are we all good up to here? All right. Let's do this last one. So if I do that one, VI, 0. VF, negative 50. Time, 5 seconds. That's all you need, right? And you get negative 125 meters. That says 125. Sorry, the screen marker is fat for some reason.
Yeah, I know.
Everybody good up to there? All right. And then you find the other ones the same kind of way. So the other answers end up being negative 20, negative 45, and negative 80. You good, or what are you guys discussing? What's going on?
Just talking about questions we got to test next hour.
Oh, gotcha.
Sorry.
You're okay. All right, everybody good? Problems, questions, concerns, anything? Dom, how you doing there? You doing all right, buddy?
Yes.
Yes? Pretty good. Jacob, you doing all right over there? Everybody happy? Awesome. All right, so now we got to fill in our number line. So I'm going to do this pretty quickly because it's just kind of marking stuff. Can I erase just to make some room on the board? All right, so I wish I had given myself a little more room here. All right. Why so small? You can make it. I hate that I can't pick the zoom level. All right, whatever. Okay, so here we go. So mark your position. So when I mark my position, which column am I looking at? Negative 10, 20, 30, or the other one? The other one, right? These are velocities. So make sure you mark the position. So the first one is 0. The next one is... What did you do? You said you did it all wrong. What did you do, just out of curiosity? That's okay. That's why we're going over it.
I marked the position. Well, first I just didn't. I did all that.
You're supposed to mark the position in case.
But I thought you just said mark the velocity.
No, I said don't mark the velocity.
Oh, never mind.
Yeah, so you were good. You were good.
I said I did all that.
Okay, so are we all good up to here, guys? Everybody good?
Yep.
All right. After 3 seconds, we're down here at negative 45. And after 4 seconds, we're down here at negative 80. That's as far as I'm going to go, just because I don't want to fight with the smartboard. But so there's our positions. And then we got to write in the velocities, right? So I'm going to do those in red, just over here where I've got a little bit more room. So velocity here is 0. Velocity here is negative 10. Velocity here is negative 20. velocity here is negative 30. I'm being sloppy about my units. Velocity here is negative 40. Did anybody notice I did something special when I drew those little red arrows?
You made their size
Longer.
I made them get longer and longer and longer to illustrate
The speed increases.
the speed increasing. It's going faster and faster. These velocity vectors are getting bigger and bigger, right? If you ignore the negatives, right? So it's going down faster and faster and faster. You should do that. I'm not going to measure them with a ruler, but I should be able to look at them and go, oh yeah, those seem like they're getting longer. Cool? Yes, Haley. Yes, that's what you're supposed to do. I just didn't because my data table was in the way. As long as you got it in there somewhere, I'm not going to get fussy about it. All right, are we good? All right, everybody. Question number 3 says, what's the acceleration? So what's the acceleration? Cool? Okay. So finally, on the back page, flip it over. Sorry, I ran the copies. We're going to turn it that way. And all we're going to do is we're going to take the two types of motion. We're going to take the horizontal motion of the bike moving at a constant velocity and the vertical motion of the bike falling and speeding up, and we're going to combine the two to create the motion graph for a bike that's traveling at 20 meters a second horizontally across a roof and then going off of the roof. And we're going to make a motion map. All right? So it says we're going to assume the corner of the roof is a horizontal and vertical position of 0. Take the numbers from parts 1 and 2 and put them in the chart. So you're literally just copying numbers. All right? So from chart 1, our horizontal velocity was always 20. Our horizontal position began at 0 and then went up by 20. From chart 2, our vertical velocity began at 0 and then decreased by 10. And our vertical position, we had to calculate. It was a pain. But these are the numbers you get. This is now the 3rd time we've seen these numbers. You should know them, or at the very least know how to get them. Good? And then plot the points down here on the graph that's at the bottom of the screen that we can't see yet because I haven't scrolled down. Which 2 columns am I going to use when I plot the points? The 2 position columns. So the last 2 columns, right? I'm going to look at horizontal position and vertical position. Follow? Everybody good with that? All right. A few people still writing. We got 5 minutes. That should be just enough to finish. Please give me those 5 minutes. You got no homework, so seems like a fair trade. 5 minutes for no homework. All right, so here we go. Let's plot our points. You got to make sound effects or it doesn't work. Move this garbage out of the way. All right, so here we go. Plot the points. So, oh shoot, I scrolled too far. There we go. Okay, so at time 0, our positions are both 0. After 1 second, we've moved horizontally 20 meters and fallen down 5 meters. After 2 seconds, we go forward another 20 meters and come down to a position vertically of 20. We go forwards 20 and down to 45. Uh-oh, that's not 20. There we go. Something like that. Go forwards 20 and down to 80, right? And then the last one is off of the board over here. So there's another dot down there that I'm not going to draw just because we're tied up time. All right, what do you notice about the dots? What's the shape they suggest? Parabola, right? That's the path that they follow. We now know where this bicycle is at any instant. Where's the bike after 2.5 seconds? Right here, right? Or whatever, right? I should have put it better. But all right, we good? All right, so the next thing we got to do is put in our velocity vectors. What are all of the horizontal velocity vectors? 20. So draw a little arrow, Vx equals 20. Vx equals 20. I'm not doing units just because I'm trying to save time. What should the units be? What do you notice about all the arrows that I drew? They're all about the same length, right? Ish. Not perfect, I didn't measure it, but good. All right, what about the vertical velocity? Let's see, it starts at 0, and then it goes -10, -20, -30, -40, and then the last one would be -50 down there off the screen. Cool. So it's moving horizontally the same amount every second, the vertical velocity changes. Are we good?
Yeah.
Last question, what's the acceleration the entire time the bike is in the air? -10 meters per second squared. There we go. Questions?